This is section 8.1, part A, confidence intervals, the basics. So in this activity, I am supposed to come up with a number and store it into the calculator, and you are not allowed to know what this number is. And then you have to estimate what this number is based on the information. So I'm going to store the number, I'm going to clear the home screen, and then you're not going to know what that value is. I'm going to give you parameters that tell you that you are going to find the mean of a random normal distribution for our value m, 20, and then 16. So this tells you you're going to do 16 observations, and our mean for the population is m, and the standard deviation is 20. And you're going to compute the mean from those 16 samples. Now, you have to determine how reasonable it is for you to guess what the mean is for the entire population based on this result. So when Mr. Shields' class did this mystery mean activity, the TI screen gave them the value of 240.79 as the mean of the 16 observations they did from the 16 samples. So here's a summary of what the class said about the calculator output. The population distribution is normal, and it has a standard deviation of 20. A simple random sample of size 16 observations was taken for this population, and the sample mean for that population was 240.79. If we had to give a single number estimate to the value of m for Mr. Shields chose, what would it be? Such a value is known as a point estimator. So what about picking 240.79, since that's what the calculator told us? That makes sense because the sample mean x bar is an unbiased estimator of the population mean mu. We are using the statistic x bar as our point estimator of the parameter mu. So a point estimator is a statistic that provides an estimate of the population parameter. The value of the statistic for a sample is called the point estimate. Ideally, a point estimate is our best guess at the value of the unknown parameter. In each of the following settings, determine the point estimator you would use and calculate the value of the point estimate. So quality control inspectors want to estimate the mean lifetime mu of the AA batteries produced in an hour at a factory. They select a random sample of 30 batteries during each hour of production and then drain them under conditions that mimic normal use. Here are the lifetimes in hours of the batteries for the sample. So we can use the sample mean x bar as our point estimate for the population mean mu. For this data, if we find the mean of all of these values, we would get our x bar is equal to 16.7 hours. So we would let our point estimate be 16.7 hours, which means we are going to estimate that the population mean would be 16.7 hours. What proportion P of U.S. high school students smoke? The 2007 Youth Risk Behavioral Survey questioned a random sample of 14,041 students in the grades 9th through 12th grade. Of these, 2,808 said that they had smoked cigarettes at least one day in the past month. So in this case, we're going to use the sample proportion, P hat, as a point estimator for the population proportion P. For this survey, our P hat value is that 2,808 out of the 14,041, which is going to give us a P hat value of 0.20. So we would estimate, or our estimator that we would use, our point estimator, would be 20%. The quality control inspectors in A, when we were talking about the batteries, want to investigate the variability in the battery's lifetime by estimating the population variance, which is your standard deviation squared. So for this one, we're going to use the sample variance, which is the standard deviation of just the sample squared, as a point estimator for the population variance, sigma squared. For the battery life data, our point estimator is that the variance for the sample is 0.508. Is the value of the population mean mu that Mr. Shield entered into his calculator exactly 240.79? Probably not. Because x bar equals 240.79, we guess that the mean is somewhere around 240.79. How close to 240.79 is mu likely to be? To answer this question, we ask another. How would the sample mean x bar if we took many simple random samples of size 16 from the same population? So how would those samples be different, and what would be the mean of all of those samples? The sampling distribution of x bar describes how the values of x bar vary in repeated samples. Recall the fact about the sampling distribution from Chapter 7. The shape, because the population distribution is normal, so is the sampling distribution of x bar. Thus, the normal condition is met. The center, the mean of our sampling distribution x bar, is the same as the unknown mean mu of the entire population, or the mean of all of our sample means will equal the mean of the population. The standard deviation of x bar for a simple random sample of size n equals 16 observations. To find our standard deviation, you're just going to do the standard deviation of the population divided by the square root of the number of samples, or in this case, 20 divided by the square root of 16, which will give us 5. Because the 10% condition is met, we actually can find that standard deviation. Remember, your sample size must be less than 10% of the entire population. So the figure below summarizes the previous facts. We have our population, we don't know what the mean is, but we know the standard deviation is 20. We are going to take different samples of size 16. So we'll take one sample of size 16 and get a mean of 240.79. We'll take another sample of size 16 and get a mean of 246.05. We'll take another sample of size 16. Remember, to do the sampling distribution, it would have to be all samples of size 16 for the entire population that are possible. From there, you will get your sampling distribution. Now, we still don't know what that mean is, but we do know that our standard deviation now, instead of 20 like the population, will only be 5, because you take the standard deviation of the population and divide it by the square root of the number of observations you're taking, which was 16. So when Mr. Shields' class discussed the results of the mystery mean activity, students used the following logic to come up with an interval estimate for the unknown population mean mu. To estimate mu, we're going to use the mean of x bar is equal to 240.79 of the random sample. This was our point estimate. We don't expect that x bar will be exactly equal to mu, so we want to say how accurate this estimate really is. In repeated samples, the values of x bar follow a normal distribution that has a mean of mu and a standard deviation of 5. So if we think back to our 68, 95, 99.7 rule, the 95 part of that rule says that x bar would be within 10 units, or within 2 standard deviations of the population mean. So if we have our mean, we know within 2 standard deviations, 95% of the data should fall within there. Whenever x bar is within 10 points of mu, mu is within 10 points of x bar. This happens in about 95% of all possible samples. So the interval from x bar minus 10 to x bar plus 10 captures the population mean mu in about 95% of all samples of size 16. So if we estimate that mu lies somewhere in the interval of our x bar plus or minus 10, our x bar, or our sample mean, was 240.79. If we add and subtract 10, we're going to get that our values should fall, the true population mean should fall between 230.79 and 250.79. We'd be calculating this interval using a method that captures the true mean in about 95% of all possible samples of this size. The big idea is that the sampling distribution of x bar tells us how close to mu the sample mean x bar is likely to be. Statistical estimation just turns that information around to say how close to x bar the unknown population mean mu is likely to be. In the mystery mean example, the value of mu is usually within 10 units of x bar for a simple random sample of size 16. Since the class's sample mean was 240.79, the interval of 240.79 plus or minus 10 gives us an approximate 95% confidence interval of mu. So all confidence intervals we will have to form in a similar way. So you're going to take whatever your estimate is, you're going to plus or minus your margin of error. The estimator, in this case, which was our 240.79, is our best guess for the value of the unknown parameter. The margin of error, which in this case will be 10, shows how close we believe our guess is. Based on the variability of the estimate in repeated samples of size 16, we say that our confidence level is about 95% because the interval of x bar plus or minus 10 captures the unknown parameter in about 95% of all possible samples. So remember that margin of error will be different for each set that you take because it's going to depend on what the standard deviation for the population is and your sample size. We're doing 95%, so that's within 2 standard deviations. Since the standard deviation of our sample was 5, because we did 20 divided by the square root of 16, and 2 times 5 gives us 10, that's why our margin of error was 10. So this will be different for each set that we look at. So a confidence interval for a parameter has 2 parts. An interval calculated from the data, which has the form of your estimate plus or minus the margin of error. And the margin of error tells us how close the estimate tends to be to the unknown parameter in repeated random samples. And it's going to have a confidence level C, which gives the overall success rate of the method for calculating confidence interval. That is, in C%, or in this last case we looked at 95% of the possible samples, the method will yield an interval that captures the true parameter value.